An eutectic system from the Greek I-micron I, and I registered trademark I3/4 I to the first I describes a homogeneous solid mix of atomic and or chemical species, to form a joint super-lattice, by striking a unique atomic percentage ratio between the components as each pure component has its own distinct bulk lattice arrangement. It is only in this atomic molecular ratio that the eutectic system melts as a whole, at a specific temperature, the super-lattice releasing at once all its components into a liquid mixture. ET is the lowest possible melting temperature over all of the mixing ratios for the involved component species. Upon heating any other mixture ratio, and reaching ET see the phase diagram to the right. 1 component's lattice will melt first, while the mixture's temperature has to further increase for the other component lattice, S, to melt. Reversely, as a non-eutectic mixture cools down, each mixture's component will solidify at a distinct temperature, until all material is solid. The coordinates defining an eutectic point on a phase diagram are the eutectic percentage ratio and the eutectic temperature. Not all binary alloys have eutectic points. In other words, the valence electrons of the component species are not always compatible, in any mixing ratio, to form a new type of joint crystal lattice. For example, in the silver-gold system, the melt temperature and freeze temperature meet at the pure element endpoints of the atomic ratio axis while slightly separating in the mixture region of this axis. Eutectic reaction. The eutectic reaction is defined as follows. This type of reaction is an invariant reaction, because it is in thermal equilibrium. Another way to define this is the Gibbs free energy equals 0. Tangibly, this means the liquid and two solid solutions all coexist at the same time and are in chemical equilibrium. There is also a thermal arrest for the duration of the change of phase during which the temperature of the system does not change. The resulting solid macrostructure from a eutectic reaction depends on a few factors. The most important factor is how the two solid solutions nucleate and grow. The most common structure is a lamellar structure, but other possible structures include rod-like, globular, and acicular. Non-eutectic compositions. Compositions of eutectic systems that are not at the eutectic composition can be classified as hypotectic or hypertectic. Hypotectic compositions are those with a smaller percent composition of species I squared and a greater composition of species I plus or minus than the eutectic composition, while hypertectic solutions are characterized as those with a higher composition of species I squared and a lower composition of species I plus or minus than the eutectic composition. As the temperature of a non-eutectic composition is lowered, the liquid mixture will precipitate one component of the mixture before the other. In a hypertectic solution, there will be a pre-eutectoid phase of species I squared, whereas a hypotectic solution will have a pre-eutectoid I plus or minus phase. Types. Alloys. Eutectic alloys have two or more materials and have a eutectic composition. When a non-eutectic alloy solidifies, its components solidify at different temperatures, exhibiting a plastic melting range. Conversely, when a well-mixed, eutectic alloy melts, it does so at a single, sharp temperature. The various phase transformations that occur during the solidification of a particular alloy composition can be understood by drawing a vertical line from the liquid phase to the solid phase on the phase diagram for that alloy. Some uses include eutectic alloys for soldering, composed of tin, lead and sometimes silver or gold, especially SN63Pb37 alloy formula for electronics, casting alloys, such as aluminium, silicon and cast iron. Silicon chips are bonded to gold-plated substrates through a silicon-gold eutectic by the application of ultrasonic energy to the chip. See eutectic bonding. Brazing, where diffusion can remove alloying elements from the joint, so that eutectic melting is only possible early in the brazing process. Temperature response, for example, Wood's metal and Field's metal for fire sprinklers. Non-toxic mercury replacements, such as Garlenston, experimental glassy metals, with extremely high strength and corrosion resistance, eutectic alloys of sodium and potassium that are liquid at room temperature and used as coolant in experimental fast neutron nuclear reactors. Others, Sodium chloride and water form a eutectic mixture whose eutectic point is a 21.2 ESHC and 23.3% salt by mass. The eutectic nature of salt and water is exploited when salt is spread on roads to aid snow removal, or mixed with ice to produce low temperatures. Ethanol water has an unusually biased eutectic point, that is, it is close to pure ethanol, which sets the maximum proof obtainable by distillation. Solar salt, 60% NaNO3 and 40% KNO3, forms a eutectic molten salt mixture which is used for thermal energy storage in concentrated solar power plants. To reduce the eutectic melting point in the solar molten salts, calcium nitrate is used in the following proportion: 42% Ca, NO3, 2, 43% KNO3, and 15% NaNO3. Lidocaine and prolecane both are solids at room temperature. Form a eutectic that is in oil with a 16 degree Celsius melting point that is used in eutectic mixture of local anesthetic preparations. Menthol and camphor, both solids at room temperature, form a eutectic that is a liquid at room temperature in the following proportions: 8:2, 7:3, 6:4, and 5:5. Both substances are common ingredients in pharmacy extemporaneous preparations. Minerals may form eutectic mixtures in igneous rocks, giving rise to characteristic intergrowth textures exhibited by granophyre. Some inks are eutectic mixtures, allowing inkjet printers to operate at lower temperatures. Other critical points: eutectoid. When the solution above the transformation point is solid, rather than liquid, an analogous eutectoid transformation can occur. For instance, in the iron-carbon system, the austenite phase can undergo a eutectoid transformation to produce ferrite and cementite, often in lamellar structures such as perlite and bainite. This eutectoid point occurs at 727 degrees Celsius and about 0.76% carbon. Paratectoid. A paratectoid transformation is a type of isothermal reversible reaction that has two solid phases reacting with each other upon cooling of a binary, ternary alloy to create a completely different and single solid phase. The reaction plays a key role in the order and decomposition of quasicrystalline phases in several alloy types. Paratectic transformations are also similar to eutectic reactions. Here, a liquid and solid phase of fixed proportions react at a fixed temperature to yield a single solid phase. Since the solid product forms at the interface between the two reactants, it can form a diffusion barrier and generally causes such reactions to proceed much more slowly than eutectic or eutectoid transformations. Because of this, when a paratectic composition solidifies, it does not show the lamellar structure that is found with eutectic solidification. Such a transformation exists in the iron-carbon system, as seen at the upper left corner of the figure. It resembles an inverted eutectic, with the I phase combining with the liquid to produce pure austenite at 1495 degrees Celsius and 0.17% carbon. Paratectic decomposition. Up to this point in the discussion, transformations have been addressed from the point of view of cooling. They also can be discussed noting the changes that occur to some solid chemical compounds as they are heated. Rather than melting, at the paratectic decomposition temperature, the compound decomposes into another solid compound and a liquid. The proportion of each is determined by the lever rule. The vocabulary changes slightly. Just as the cooling of water, which leads to ice, is termed freezing, the warming of ice leads to melting. In the AL or phase diagram, for example, it can be seen that only two of the phases melt congruently, or AL2 and or 2Al. The rest paratectically decompose. Eutectic calculation. The composition and temperature of a eutectic can be calculated from enthalpy and entropy of fusion of each components. The Gibbs free energy, G, depends on its own differential. Thus, the GT derivative at constant pressure is calculated by the following equation. The chemical potential is calculated if we assume the activity is equal to the concentration at the equilibrium, thus is obtained by using and integrating Gibbs. The integration constant K may be determined for a pure component with a melting temperature and an enthalpy of fusion ek. we obtain a relation that determines the molar fraction as a function of the temperature for each component. The mixture of n components is described by the system. That can be solved by. See also, azeotrope, constant boiling mixture, freezing point depression, references. Bibliography, Smith, William F. Hashimi, Javad, Foundations of Materials Science and Engineering, McGraw-Hill, ISBN A0-07-295358-6. Further reading, Askland, Donald R. Pradeep P. Puel. The Science and Engineering of Materials. Thomson Engineering. ISBN A0-534-55396-6. Easterling, Edward. Phase Transformations in Metals and Alloys. CRC. ISBN A0-7487-5741-4. Mortimer, Robert G. Physical Chemistry. Academic Press. ISBN A0-12-508345-9. Reed Hill, R.E. Reserboyan. Physical Metallurgy Principles. Thomson Engineering. ISBN A0-534-92173-6. Satterway, Donald. Phase Equilibria and Phase Diagrams 3.091 Introduction to Solid-State Chemistry, Fall 2004. MIT OpenCourseware. Archived from the original on October 20, 2005. Retrieved April 12, 2006. A.